Hello, everyone. This is the first session, and it's the step into data reduction techniques. And this session will give the introductory information on reduction techniques and introduce one of the well-known applications of such techniques, and it's known as data deduplication. Data deduplication and other methods of reducing storage consumption play a vital role in affordably managing today's explosive growth of data. Optimizing the use of storage is part of a broader strategy to provide an efficient information infrastructure that is responsive to dynamic business requirements. This presentation will explore the significance of deduplication from both the theoretical and practical aspects related to specific capacity optimization techniques within the context of information lifecycle management, the benefits of optimizing storage capacity span, cost savings, risk reduction, and process improvement. Capital expenditures on networked storage equipment and floor space can be reduced and deferred by data reduction techniques. Ongoing operating expenses for power, cooling, and labor can also be reduced because there is less equipment to operate and manage. Increasing the efficiency and effectiveness of their storage environments helps companies remove constraints on data growth, improve their service levels, and better leverage the existing and increasing quantity and variety of data to improve their competitiveness. Okay, I'll start with a quote from the reference below. It says, "It's estimated that the combined technological capacity of the world to store information provides 1,300 exabytes of hardware digits in 2007, but when the corresponding content is optimally compressed, this only represents 295 exabytes of information. This amounts to around 4x more space to store new information." This estimate is quite motivational here, and it shows that it's worth to learn more about techniques that enables compression of data. And that's why you're here, and that's also why I talk about data reduction techniques today in this session. All right, so here is a big picture. There are 4 major data reduction techniques as shown. I tried to draw them at scale such that their relevance can be inferred from the Venn diagram. It's important to note that significant storage space savings is possible when all of the data reduction techniques are used judiciously and in correct order. I will try to touch upon file compression techniques first in the next couple of slides, but the number of slides about this subject is huge. Actually, not the slides, but the studies. But the main intent of this video is not to cover these studies in detail, but I urge to find more information about these studies on web at your spare time. Personally, I thought it's pretty interesting to watch how this subject has evolved over the years. On the other hand, as you can see, there are 4 of them: deduplication, copy on write, TIM provisioning, and file compression techniques. The TIM provisioning, deduplication, and copy on write, on the other hand, they are closely tied technologies and shall be covered in order as shown here in this session. I'll give only brief information about the provisioning and why it's being used, and introduce the details of deduplication right after it. Copy on write will be mentioned when we discuss source deduplication, and I want to explain what the word deduplication means here, because I'll be using it over and over again without giving the details for the next couple of slides. As you might know, duplication is about creating new replicas. In other words, we create a new copy of the data. Deduplication is the exact inverse operation of deduplication. In other words, it identifies same set of copies and store only one of them. So it's also store once concept. That's why it's also known and well known with the name single instance storage. Okay, so here I picked up some of the industry leaders who have invested great deal of effort and finance on the development of the data reduction algorithms in the past 10 or 20 years. Since petabytes of storage savings are at stake, it means a lot of money can be saved, which leads to industries to put more effort on this subject matter than anyone else. All that summed, it's no surprise that one of the well-known data reduction techniques, deduplication, is a highly proprietary technology. For instance, Microsoft has a patent on single-instance storage. In addition, Quantum owns a patent on deduplication. One of the latest technology is known as progressive deduplication, for example, by Archaea, which is not listed here. But is now owned by Western Digital, and it's a more efficient technology. But please don't worry about the names at this point or terms, as we will talk about them later in detail on the next session and so on. The main message here is that although we will give general enabling technologies for good data reduction, the details are implemented quite differently by different vendors. And industry is a driving force for better deduplication, better data reduction. Deduplication is a maturing technology. In fact, deduplication is becoming a standard feature of backup and archival systems, file systems, cloud storage, network traffic optimization, and in other words, it's no longer offered as an additional feature, but rather it comes with the basic package. What's more striking is the fact that data deduplication typically provides up to 100 by 1 reduction of backed up data by eliminating duplicate copies of data, as evidenced by the study reference below. Here's the outline of this video series. This is not just the outline for this session, but it's a couple of sessions. But I just decided to give all the outline over here. In this session, we will start with the fundamental information theoretic question: where did it all start? We'll start discussing compression in general, then compare and contrast with deduplication, the single instant storage or instant storage. We'll cover the working principles of deduplication, type of deduplication, and the building blocks if one wants to implement a deduping engine to be integrated inside their system. Later in the series, we'll consider details about the internals of deduplication, namely chunking, indexing, and relevant problems such as disk bottleneck problem and hash collisions, and also solutions, such as one of the well-known techniques called Bloom filter can help with that. And later in the series, we'll give details on more advanced topics that go under names protected, secure, and progressive deduplication. We'll actually have a little slide in this session about progressive deduplication. But if you want to learn more about this technology, I'll urge you to go and search for this progressive deduplication name on the web. All right, so data compression. It all started with Shannon. Data compression, as I said, is a neat and long theory. It is mathematically quantified in Shannon's 1948 seminal paper for the first time by introducing concepts like entropy of a given source. Sources are treated as random variables, and then people ask questions like, what's the entropy of the source? And it's shown, for example, one of the striking results of his paper was that a given source cannot be compressed more than its entropy. This theory and the results associated with that theory is known as information theory and sparked a lot of attention after its first release date. The goal of compression is to eliminate redundancy or undesired data. There are two types of compression: lossy and lossless. In lossy compression, the source is compressed based on a distortion constraint. Since most multimedia sources carry more information than we can perceive, the redundancy can be taken out, leaving a compressed and yet meaningful information to be stored. JPEG, SPITE these are known lossy image compression techniques. You can type in, on your browser and search for them to get to more information. You can find thousands of these techniques for video compression as well. Lossless compression, on the other hand, does not lead to any form of distortion. Exact reconstructibility is guaranteed. I don't know if reconstructibility is a word here, but I'm just using it. I'm hoping that you guys understand what it means. PNG, GIF formats are lossless compression examples. Particularly important application of lossless compression is for the computer data, such as Lampel, Welch algorithm or zip algorithms. Lossless compression is crucial for computer data because any loss will lead to loss of conceivable data. As you might guess, deduplication as defined so far is not an alternative to any one of these compression algorithms, but rather it is a complementary data reduction framework. So that's important to make this distinction between deduplication and compression. That's why I'm mentioning about compression in this slide. Alright, so let us consider a motivational example. A text compression algorithm called Lampel Welch will be the one that will be given an example of. The text is to be or not to be, or to be or not. If you put this text through LZW compression, it partitions and encodes the text at the same time. It creates a dictionary of letters first, and then combination of letters to create strings, and each string is encoded using a binary code. Alternative to this text compression technique is to perform the chunking, or breaking the text into subtexts or strings, that's what we call chunking, and then encode it later. As you can see, there are two options shown that breaks the text into similar strings, but this time longer than the ones that LZW creates in general. LZW is a compression algorithm, and it does not get rid of the replicated data so easily. As apparent from both options here, if you run a deduplication algorithm that identifies the identical chunks first, it breaks the text into subtext, and then identifies them, and then stores them only once. In other words, stores the unique ones. You will have a great potential for compression. There are a variety of file types that generate such content, by the way, and hence it's a perfect match for deduplication. I also want to talk about another useful technique as part of data reduction techniques. Theme provisioning is a data reduction technology usually used in almost every virtualized system to give the appearance of having more physical resources than are actually available. If a system always has enough physical resources to simultaneously support all of the requests, then it's not theme provision. The provisioning is particularly suited and very useful if the system cannot predict the amount of resources that is being requested at the time of resource allocation. In storage world, due to this fact, using theme provisioning, storage capacity utilization efficiency can be automatically driven up towards 100% with very little administrative overhead. An example is shown here with various geometric shapes representing different clients requesting resources and storage, and the storage system allocates 33 terabyte space, although the physical available storage space capacity is 25 terabytes. This is done because experimentally it's known that only 10% of the requested amount is used over the course of the requested resource lifetime. Although I already described what deduplication means in simple terms, here I jot down few notes on what it's known as. It's called intelligent or single instance storage, as I mentioned that before. This name is actually coined as a term that Microsoft or later IBM used in a typical deduplication scenario, and only one unique instance of data is actually retained on storage media. What happens is that when the redundant data is identified, it is replaced with a pointer to the original copy. The figure here shows an example of compression and deduplication operating on the same system. As can be seen, as long as we use the same compression algorithm, the compressed outputs will be identical, and hence deduplication can be applied across files to gain data reduction. So deduplication can be provided at the file level or at the block level or chunk level. Block level is deeper search than file level because it involves recognizing the file as a string of symbols, and then the string is divided into fixed and variable length blocks. File level compression is simpler because it's easy to identify identical copies, and the number of files is smaller than the number of blocks or chunks, and we store only unique files or unique chunks. At the block level, the number of blocks to manage increases as we have more and more distinct files because they don't share many blocks with each other. It gets harder to figure out identical blocks, which means more processing power is required. However, block level compression provides smaller grain accuracy and hence better compression efficiency. The computation time, of course, may lead to latency issues associated with deduplication systems. Later, we will cover advanced techniques such as progressive deduplication that offers a good trade-off between compression and latency. Let's look at how the data is generated in real life. For instance, we as human beings usually generate almost identical files. In other words, we we create the data, and then we change the data a little bit and then store it as a new file. So this will make file duplication not very efficient. As mentioned earlier, block level deduplication looks within a file and saves unique iterations of each block, which means far more potential exists there. However, this efficiency comes with more CPU cycles. Data reduction techniques like deduplication in particular can reduce storage capacity needed for a given set of files. The rate of transfer in communication application, for instance, that's also another potential area where deduplication can help. It will also reduce, may also reduce the network congestion, and in other words, it will ease the routing problems in computer networks. So that's particularly why deduplication is so popular these days. Okay, so how does it work? As it might have been clear by now that we need to determine the block boundaries first, this operation is called chunking. There are various algorithms that does that, but I defer the discussion on them for the next video or so. Next, files or blocks are compared. How? Well, one way is to compare them bit by bit. However, this is quite costly from computational perspective. Next option is to use hash-based comparison. In that technique, chunks or chunk contents are hashed. There is a hash function that takes this chunk content as an input and then generates some number. So these chunks are associated with hash numbers, for instance, a 128-bit word, as shown in this slide. If you compute this hash value for each block, unique data can be identified by comparing these hash values, for instance, by storing them in a lookup table. That's just an implementation detail. Yet then another approach to hash-based deduplication is called delta differencing. In that method, a base copy is retained or chosen, and all data generated from the base are identified and only difference is stored. This is very much similar to delta coding if you're familiar with JPEG compression algorithm. And in hash-based deduplication, hash values or signatures are stored in an indexed table, usually maintained in memory. When new chunks arrive, they are deduplicated based on the index table we keep in the memory, and this part is a bit of an implementation detail, but I just wanted to mention it. Okay, so we can classify deduplication either based on the time of application or point of application. Depending on when the chunking and the hash calculations are done, deduplication can be inline or post-process. If it's performed all in real time, it's known as inline. On the other hand, in post-process deduplication, data is first stored on the storage device and then processed at a later time. Then we process it at a later time and we'll analyze the data, for duplicates. But that happens after some time later. Depending on where the data is, deduplication can happen at the source, close to where the data is created, or it can happen at the target, in other words, where the data is eventually stored, or that's the final destination of the data. A simple illustration is depicted to the right of this slide, and as can be seen, storage and deduplication takes place in different orders, depending on whether it's inline or post-process deduplication process. Let me give you an overview of source deduplication. In source deduplication, all the compression and data reduction operations takes place at the source, and this is usually embedded inside a managing software or a file system. For instance, the example that I'm showing here is a file system case in which you have directories labeled as blue rectangles, and inside those rectangles you can see various geometric shapes representing the files. When we run the deduplication engine, it will figure out the orange circle is shared by different directories, and hence only one file copy will be stored. And the directories that share this orange circle will have symbolic links to the original copy. So these links are not like hard links. Symbolic links is just like it's an implementation. It's just a feature of file system. You can use it to point to the right destination, right place. As we replace all copies with symlinks, we will be able to reduce the amount of data stored on disk, while the content of metadata grown by this operation also. So that's also another consideration. Yet in another example, suppose that the same orange circle that is shared by top rectangle is modified by the user. And that becomes purple circle, indicating that it's not the same file, but it's a modified version of the same file. The case is usually handled by removing the symlink, okay? And that's the first thing you do. Copy the original orange circle to in place and apply all the modifications to the copy to generate that purple copy, okay, which is the modified version. The original orange circle stays intact and continues to serve as the base copy for all other symlinks generated by the duplication engine in the past. This way, we will keep the data reduction efficiency at an acceptable level, even if you have a modified version. So this method is quite popular in storage systems and is known as copy on write. All the ideas presented here, by the way, can be applied to sub-file level, and we further gain more efficiency in storage savings. Let us also explore a little bit of a target deduplication, which can either be inline or post-process and performed at the chunk, in other words, sub-file level. There are two options, fixed size chunking and variable size chunking. A fixed length block approach, as the name suggests, divides the file into fixed size length blocks and uses a simple checksum based approach, could be MD5 or SHA or other type of hash function, to find duplicates. Although it is possible to look for repeated blocks, the approach provides very limited effectiveness. The reason is that the primary opportunity for data reduction is in finding duplicate blocks in two transmitted data sets that are made up of mostly, but not completely, of the same data segments. For example, similar data blocks may be present at different offsets in two different data sets. In other words, the block boundary of similar data may be different. This is very common when some bytes are inserted into a file, and when the changed file processes again and then divides into fixed length blocks, all blocks will then appear to have changed. Therefore, two data sets with a small amount of difference are likely to have very few identical fixed length blocks. So this is kind of an error propagation. And it's the problem with the fixed length window or fixed length chunking. This error propagation can be mitigated by using variable size chunking, right? That's an alternative way of doing it. In that case, the offsets can be detected and hence the identical blocks that are shifted along the file can be found. This leads to better data reduction efficiency, apparently. One of the latest technologies related to deduplication is known as progressive deduplication by archival corporation, and which is now owned by Western Digital. You can Google it, and it accesses a lot of information about this technology on the Western Digital website. This is not dramatically different than fixed size chunking approach that we have seen already, but it's an alternative to variable size chunking algorithm in that you still use fixed size, but the window shifting is now part of the algorithm. As we mentioned before, variable size chunking is computationally expensive. Why? Because we determine chunks boundaries by sliding a window. We have not seen that much of a detail yet, but bear in mind that sliding a window at byte granularity and for each shift calculating a hash value for boundary detection purposes is quite a costly operation. Main motivation for progressive deduplication is that we use a fixed predetermined window size throughout the file, and we move the window for identification of identical chunks only if we do not have a match and the window search is constrained to be no more than a chunk size. An example is shown in this slide. We begin with orange window on top. If no match is found, we move the window down below, depicted as dotted red window or red chunk. As we move down, we check if we found an identical window that already exists. If found, we stop and we count both the orange and the dotted red window at the same time as being two distinct chunks. So we add them into our lookup table. If no match is found throughout the byte granular shifts of the window, we treat the next window of the same size as being a distinct chunk and add its information to the chunk database or lookup table. As we continue for search identical chunks until we hit the end of the file. One of the other contributions of this technology is that the chunk window size is fixed for the file, but it's predetermined based on the file type. So we can use different chunk size for different files. For instance, multimedia files, maybe it might be good to have large window. It might be preferable to have large window. And for other types of files, maybe we will prefer, smaller windows. So we will have more discussions on that when we get to advanced topics on deduplication. So let us draw a large, big tree to indicate different types of deduplication, how they can be gathered under different umbrella terms so far covered. As you can, see that the data deduplication can be viewed as source or target deduplication, and source can be seen as backup type deduplication, whereas target takes place in storage appliances most of the time. That's where the data lands eventually. The target can be either inline or post-process depending on when it does take place in time. Source inline or post-process duplication can be either at file or sub-file level. So we've got this branching. This choice is usually depends on the data type, storage frequency, the frequency of these files being accessed, stored, or modified, and how much efficiency is required is also another criterion. Finally, the sub-file based deduplication can be using either fixed size or variable size chunking, and progressive deduplication can be seen as a special case for fixed size sub-file deduplication. Storage capacity is the number of bytes that can be stored on a storage medium. The total or raw storage capacity of a disk drive is based on the number of sectors available for data storage. The usable storage capacity of a storage system is less than the aggregated raw storage capacity because it accounts for overhead such as spare drives, the protection due to other redundancy, and other form of resilience, partitioning, file system formatting, and staging areas used by post-processing data duplication technologies. Don't worry about these details. So in order to have an idea about how much efficiency deduplication adds into the storage capacity savings, we should define a metric to quantify it. A data deduplication ratio is the number of bytes input to a data duplication process divided by the number of bytes that are coming out. We express this ratio as dp by 1, or data deduplication ratio by 1, also known as space reduction ratio. For instance, if the raw data consumes 100 gigabyte user data and after deduplication it consumes only 10 gigabytes of data, then the ratio will be expressed as 10 by 1. I hope that with this example that it's apparent, it's obvious what deduplication ratio means and how we express it. So let us put some numbers in perspective to understand what these numbers mean. Here's a table left, on top and left column shows the deduplication ratio, and right column it calculates the space reduction percentage. In other words, the percentage of this space saving. This space saving can be calculated as 1 minus 1 over space reduction ratio. That is to say, the percentage of space reduction is calculated as 100% less the inverse of the space reduction ratio. It may not be immediately apparent, but as shown with this table, that relatively low space reduction ratios indicate significant space savings. We also plot the disk savings versus deduplication ratio in the figure below. We observe that wide range of space reduction ratios masks the diminishing returns, which is calculated in the table above, and this is illustrated in the figure below. As illustrated, deduplication ratio increasing beyond certain point does not mean we save a lot of space on disk. Okay, that's, I think, one of the takeaways from this slide. One of the interesting questions you might ask whether all data is dedupable. This is a term used to indicate dedupable is a term that is used to indicate if all the data can be deduplicated and yet achieve large deduplication ratios. Let us take office documents. They are frequently copied and distributed, so a little change in an office document causes the entire file to be stored again. So we would expect it to be dedupable. Email backups are likewise. They are dedupable. On the other hand, data derived from natural resources is not very much dedupable. Also, pre-compressed or encrypted data is usually not dedupable. This is usually because compression takes away the redundancy from the data, right? And we need redundancy to be able to have good deduplication ratios. An encryption process targets at generating non-repeating data patterns for security reasons. So that's not what deduplication is desirable for. We'll talk more about the security issues in our advanced class on deduplication later. We note also that Frequent update, copy, or append operations may make it more difficult for identification of duplicate data. Therefore, it will reduce the deduplication ratio. So in summary, main building blocks of modern deduplication systems consist of content-aware chunking, which can either be fixed or variable size chunks. We can furthermore put constraints on the minimum and maximum chunk sizes. Another building block is a chunk lookup table and the place we store that table. We'll see that even a simple lookup operation might get too complex for large tables. So there are efficient methods for making these operations simpler. And also, this hash collision problem that I just talked about earlier. And there are efficient methods to resolve this, and one of them is the balloon filter, and we'll probably cover more detail about this technique in the next video or so, and that we will give details about it. The final building block is called the reconstruction operation, which involves file receipt, right, the pointers and the other metadata, and also original blocks, unique blocks, to be able to reconstruct the file, and finally to be able to have a compression. Right, the file compression. So we'll touch upon these blocks later in our future classes. So please forward any questions you may have to me, or use my email to reach out to me. So I guess I'll be able to answer your questions through that channel. And I guess that I'll see you next time with more details about the deduplication technology and enabling techniques for more compression. Please also take a look at these references and search for keywords you have learned here to be able to get to more information on web. And see you then.